There's an entire universe hidden from our view, teeming with life in a single drop of water, holding the secrets to our own biology. And to see it, we need a special kind of eye. So in this explainer, we're going to break down exactly how a microscope works, from a simple lens all the way to the quantum realm.
So let's start with something you've probably seen 1,000 times. Maybe you spill a little water on a book or a newspaper, and for a second, the letters right underneath that drop look bigger, sharper. It's like a tiny, everyday magic trick.
Well, it turns out that little bit of magic isn't magic at all. It's just physics. You see, the curved surface of that water drop acts as a lens, and it bends the light that passes through it. And that simple principle? That's the absolute foundation for every single microscope ever made. Our own eyes are incredible, don't get me wrong, but they do have a limit. They can only resolve details down to about 1/10 of a millimeter. Anything smaller or closer together than that just mushes together into a blur. To see beyond this limit, we need to get our heads around two really crucial concepts. Okay, first up is magnification. This one's pretty straightforward. It's simply the power to make things look bigger. So if a lens has a magnification of 10x, it makes the image seem 10 times larger than it really is. Easy enough, right? But magnification is nothing without resolution. This is all about clarity. Think about a picture in a newspaper. To your naked eye, it just looks like a solid image. But with better resolution, say a magnifying glass, you can see it's actually made of thousands of tiny separate dots. Higher resolution means you can distinguish smaller details. It's the difference between seeing a blur and seeing the truth. All right, let's dive into this and start our journey with the very first big leap in seeing, the simple microscope. A classic magnifying glass, a hand lens, is really just one single convex lens. By using that curved surface, we give our eyes natural resolving power a huge boost. And suddenly we can see those tiny dots in the newspaper photo, details that were completely invisible to us just a moment before. So a single lens is a great start, for sure, but it has its limits, which leads to a pretty logical question. What happens if you start combining them? What if you put one lens on top of another? And that's exactly what pioneers like Zacharias Johnson did back in the early 1600s, creating the very first compound microscope. But it was Anton van Leeuwenhoek who really blew the doors off reality. With his surprisingly powerful single-lens microscopes, he discovered a world teeming with what he called animalcules, tiny living things in a single drop of pond water. And just like that, the field of microbiology was born. Okay, so let's level up. This idea of combining lenses leads us straight to the compound light microscope, the tool we all recognize from science class. Now, the real genius of the compound microscope is that it doesn't just add the power of its lenses together, it multiplies them. You've got the eyepiece you look through and the objective lens right over the sample. So, for example, a 10 eyepiece combined with a 40x objective lens doesn't give you 50 times magnification. Nope. It gives you 10 times 40 for a total magnification of 400 times. And using one is a very specific process. The key is to never, ever jump straight to high power. You always start wide on the lowest power just to find what you're looking for. Then you use the big knob for a rough focus and the little knob to get it perfectly sharp. And only then do you switch up to high power to see all the incredible detail. Let's see this in action. Here are some human cheek cells viewed under low power. I mean, you can kind of see they're there, these little dots scattered around, but there's no way to make out any real detail. And now, look at that. When we switch to high power, those vague little dots suddenly resolve into distinct cells. You can actually see individual structures inside them with so much more clarity. Now that is the power of compounding lenses. A really powerful light microscope can magnify an object up to 2,000 times its actual size, and its resolution is about 500 times better than our own eyes. With this, we can see bacteria, the components of our blood, even the structures inside a plant cell. This power is incredible, but even it has a fundamental limit. You see, if an object is smaller than a wavelength of light, light literally can't see it. It just passes right by. And that means things like viruses are completely invisible to even the absolute best light microscope. So, to see even smaller, we have to abandon light altogether. We need a completely different tool that plays by a completely different set of rules. And this is a huge conceptual shift. An electron microscope doesn't use rays of light at all. Instead, it fires a focused beam of electrons at a specimen. And because electrons have a much shorter wavelength than light, they can resolve incredibly tiny details, blowing right past the physical limits of light. And the increase in power? Well, it's staggering. An electron microscope can magnify an image up to 500,000 times. That is a true quantum leap beyond anything possible with light. And this isn't just about a bigger view. We're talking about a view into a whole other reality. With these machines, scientists can see the intricate machinery inside a cell, the detailed surface of bacteria, and for the very first time, something as small as an individual virus. So, why does all this matter? Let's kind of recap this journey in resolution to really understand the scale of what we've achieved. Just look at these numbers. Our naked eye can distinguish 2 points that are 1/10 of a millimeter apart, okay? A light microscope takes us all the way down to 2/10,000ths of a millimeter. And the electron microscope, it can distinguish points that are just 1/1,000,000th of a millimeter apart. That's a scale that's almost impossible to even wrap your head around. And the main takeaway here is how this technology underpins so much of our modern world. Seriously, every time you hear about medical research on viruses, or new breakthroughs in genetics, or even crucial evidence found at a crime scene, you can bet the microscope is the silent hero making it all possible. This incredible journey of discovery, from a simple drop of water to a beam of electrons, has constantly expanded what we even consider to be reality. And it leaves us with one final, exciting question to think about. What comes next? What will we invent to finally see the things that are still invisible to us today?